Now, one of the reasons we're interested in independence is that it makes our calculations of probabilities much, much, much easier. So when events are independent, then calculations that would otherwise be very hard become very easy. So let's look at some examples. So suppose we've got a computer that's producing a series of random bits. So we've got a probability p that we get a 1 and probability 1 minus p that we get a 0. So it's a bit like a coin toss. Heads is 1, tails is 0, but now it's not fair. We've got probability p of getting a 1 that needn't be a half. And we're going to suppose they're independent. So let's ask, let's consider the event that the first n bits are 1s, and then we get a 0. So we get a run of n 1s followed by 0. What's the probability of that? Now, if we did our counting, we'd have to count all the different ways that we can get the sequences that can happen and divide by the all possible sequences of n plus 1 bits. But here's an easier way. Because they're independent, we know the probability that we get the first n 1s is just the product of all different probabilities. So it's the probability that the first bit is 1 times the probability the second bit is 1, and so on up to the probability the nth bit is 1. Now, all of these are the same probability, right? P. So we're multiplying p n times, so it's p to the power n. So we can just write that down directly. We don't need to do any of our counting or anything. So our independence makes that much easier. And then the probability that the n plus 1th bit is 0 is just 1 minus p. It doesn't depend on what happened before. And so the probability of E is the probability of n 1s followed by a 0 is just p to the n times 1 minus p. And so we can do these kind of calculations that would otherwise be quite hard become really very easy. Let's look at some other examples. Coin flips, which is basically the same setup as before, with the probability p that we come up heads. So the probability that we get n heads on n coin flips is p to the n, just like before for the ones. Probability of n tails on n coin flips is 1 minus p to the n, right? The probability of a tail on each flip is 1 minus p. And then to get it on n coin flips, we just multiply them up n times, which is 1 minus p to the n. Because they're independent. Of course, it's not true in general, right? It's not true if they're not independent. We're using independence here to make our calculations easy. So then we can ask, what's the probability that we get k heads and then n minus k tails? Well, we just multiply. So we've got p to the k, it's probability of getting k heads, times 1 minus p to the n minus k. So that's the tails. And that's the probability of a particular sequence, right, of k heads followed by n minus k tails. Suppose we don't care about the ordering. So now instead of considering a permutation like there, we're interested in a combination. We're just interested in what's the probability that we get k heads on n flips, and we don't care about the ordering. Well, we're going to have the same setup. So the fact that the ordering doesn't change the probabilities of the individual sequences, right? There's still going to be p to the k, 1 minus p, n minus k is the probability of each different permutation, and there's n choose k permutations. So the probability is n choose k, p to the k, 1 minus p to the n minus k. And so you should pay some attention to that. That kind of calculation is one that's going to come up again and again and again. Here's another example. Suppose we've got our phone, which has a cellular and a Wi-Fi interface. Suppose the probability that the cellular interface is working is P1, probability the Wi-Fi is working is P2, and we're asked the question, what's the probability that at least one interface is functioning? Now, whenever you see the at least, that's a hint, usually, to try and calculate the opposite thing and then take 1 minus. So let's calculate the probability that both interfaces fail, and then take 1 minus that, and that'll be the probability that at least one is working. The probability both interfaces fail is the probability that LTE fails times probability Wi-Fi fails, because these are independent by assumption. So we just multiply probabilities, it's nice and easy. So that's 1 minus P2 is the probability LTE fails, because P1 1 minus P1 is probability LTE fails because P1 is probability that it's functioning. 1 minus P2 is probability the Wi-Fi interface fails. And then we take 1 minus that. So there's lots of 1 minuses here, but it's still very straightforward. We can do the same calculation using hash tables. I'll let you look at that in your own time. It's just exactly the same setup, except we can allow different probabilities for all different events. Sorry, this is the example, with probabilities for the different events being different, but I'll let you work through that in your own time solve. It's basically the same setup as before. So here's a word of caution about independence. Independence is great when it holds because it makes our life very easy when doing calculations. But you know, time is very rare. It's not clear that independence ever really holds, to be honest. It's more that you're making an assumption or an approximation when you're assuming independence. So why am I saying it probably doesn't ever hold? Because time moves on and the world changes. You know, the universe evolves or changes over time. And so if we carry out an experiment now and then carry it out in a week's time, things might have changed. And they might have only changed a little bit, in which case maybe your assumption is fine, of independence is fine, but they might have changed a lot. And so, for example, if it was the stock market and there's external events happen, then maybe there's big changes. You know, if there's been a crash, the events before and after a crash are not depend on each other, right? The order will depend on the fact that the crash happened. The probabilities will depend on the fact that the crash happened. And so the fact that they won't be independent, there's loads of examples of that sort of climate change. You know, you think the weather doesn't change that much from day to day, and it doesn't. But over a period of time, it is changing because we've got climate change happening and the environment's changing, and so on. So the time scale we look at matters when thinking about independence, and it's worth being quite cautious about independence. It probably doesn't generally hold, but sometimes when we can say that it approximately holds, then it's very convenient. And so because it's so convenient, it's a really common assumption, but it's worth being wary of. And here's one of the reasons to be wary of it. Suppose we're interested in mortgages, and we suppose the probability that a given household defaults on the mortgage is 1 in 100. If we've now got two households and we assume the probability of them defaulting is independent, then the probability that both households default is 1 over 100 by 1 over 100, which is 1 over 10,000. And then if we've got 3 households, it becomes 1 in a million, and so on. And if we start having many households, then we get the probability that they all default becoming really, really small really quickly. But what if the assumption is wrong, right? It's a fragile assumption. When you're getting very small probabilities, you should always wonder, are they reliable? Because are they somehow fragile? Because what if the independence assumption is wrong, then these probabilities might not be anything like as small as you think they might be when independence holds. So for example, suppose it's a town, there's a large employer that employs loads of people, right, and closes, then the probability of 3 households defaulting might be really high, much higher than 1 in a million, right? Might be really quite high indeed. And so it's worth being careful when you use independence to say that events are really rare, for example, because if there's any correlation between events, they might be far less rare than you think, and they can mislead you if you start to rely on that. And of course, this is part of what underlay the subprime crisis back in 2008. This kind of thinking, an assumption that mortgage defaults were independent. Therefore, if you bundle up a set of mortgages, the probability of lots of them defaulting is really low if they're all independent. But of course, they're not independent if there's a correlated effect like an economic crash or a change in sentiment. Then they can all fail simultaneously with much higher probability than you'd have predicted, and so you're left with the problem. There's another example that's worth being aware of, is that in crypto there's often relies on random number generators, and we'll come on to random number generators shortly. But there's an assumption that it produces independent samples. And if that's not true, then a lot of your crypto fails. So you want to be careful to construct random number generators that are drawing independent samples, or a lot of your security that's built on that will fail. And that's actually a way of attacking the crypto, is try and undermine the random number generator so that the samples become correlated, and then it greatly weakens the crypto. And in fact, that was essentially an attack carried out by the NSA against the standards bodies, the crypto standards bodies. They used a weak random number generator that compromised all the crypto for a while, until it was changed.